Hello, everyone. This is Qixing Wang from the Department of Computing, Hong Kong Polytechnic University. Today, I want to cut in from the angle of CPS software engineering to talk about how hybrid automata technology can contribute to address the design challenges and testing challenges, two very important problems in CPS software engineering. I want to first give you a big picture on the CPS software engineering challenge, the problem space, and then I will talk about the specific case studies to show how hybrid automata technology can contribute. So we all know CPS is the inevitable result of computing infiltrating nearly every physical domain. And many interesting CPS systems are mission critical or safety critical, like avionics, medicine, robotics, etc. And for mission critical and safety critical CPSs, the key challenge is actually, from my opinion, is actually software engineering. The major problem is that the developers, they lack the other domains knowledge. Okay, so what does that mean? CPS are inevitably involving multiple domains, at least computing and another physical domain knowledge. In order to develop such systems, we need knowledge background, not only in computing, but also from the other physical domain. For example, if we are going to build a surgical robot, so who is qualified to write a program of such a surgical robot? I myself has been working in the IT industry for how many years? Nearly 30 years, counts ever since my high school. Okay, but if I write the program to cut open your heart, do you dare to use it? Okay. I would say no. Definitely not, because I lack the background in surgery. I'm not a doctor. I'm not a medical doctor. So on the other hand, are those surgeons qualified to write the program for surgical robots? It's neither, because they lack the knowledge in programming, programming language. So this is the dilemma in developing CPS systems. So we need experts from every domain, and very few of these experts can know everything. Okay, so finally, we have a bunch of less qualified people to build up a mission critical and safety critical systems to run. This is a very dangerous practice, and this causes a lot of problems. For example, the Boeing 737 MAX 8 accident. Okay, so it's now widely believed that it's because of one of the software design issues. Okay, so people violated the rule in avionics, the redundancy rule, which resulted in this disaster. And also, there are many other examples. For example, last year in Hong Kong, the subway system had an accident. The reason is also because of the CPS software. The people who wrote the control software for the subway train, apparently they are not familiar with the railway scheduling practice. So at the crossway, there are some mutual exclusion protocols that you have to follow, but the software failed to follow that, and this causes the crash. Fortunately, it is during the testing phase, not in the real practice, but still it causes millions of dollars of loss and days of halted operation. So how to address these challenges? So as academians, we need to look into the problem space. I believe the CPS software engineering implies a huge problem space for us. Actually, it's also huge opportunities. we have three dimensions for this problem space. One of the dimension is the application domain. Okay, so for different kinds of CPSs, we need different kinds of domain knowledge. Medical CPS, control CPS, smart building, okay, smart transportation, power grid. Okay, so they, all of them, they involve their unique kind of knowledge background. Another dimension is a dimension of various software engineering tasks. Okay, so this is not just for CPS, this is for software engineering in general. We talk about these four fundamental activities: requirement engineering, to understand users' demands and constraints. Okay. And then after that is the design activity, design and implementation activity. So this involves course design, the high-level design, the detailed design, and it also involves implementation. And then it involves the activity of validation and verification. So verification is about building models, for example, to prove the mathematical model is correct. And also testing is also considered part of the verification. In testing, we need oracles from time to time to predict or to label the correctness of the output given a test case input without looking into the source code. We need to judge the correctness of the output. This is the job of oracles. And then testing, if we find there are faults in the software, then we need to remove these faults. So it's called debugging. And then another category is deployment and evolution, software evolution, maintenance, deployment, maintenance, and runtime dependability. So many tasks in software engineering perspective. The third dimension is various kinds of computer science areas, various kinds of technologies in computer science that can be exploited to solve the specific software engineering issues in different kinds of CPS. Okay, so for example, formal method, design pattern, AI-related technologies like machine learning, system identification, data mining, even natural language processing, information retrieval, or even computer vision, okay, can they contribute? Real-time is definitely one of the computer technologies that are closely related to CPS, networking, security, etc. So these three dimensions expand a huge problem space for CPS software engineering research. Okay, so basically using various kinds of computer science technologies to address specific problems in CPS software engineering, and which needs to exploit, needs to comply with certain physical domain knowledge background, okay, managed knowledge domain. Okay, so just look at these three dimensions alone. There are already hundreds of topics to dig in. Okay, so there's almost endless job to explore. And unfortunately, in the past 10 years, my research group have been working on several of very exciting problems in this problem space. But because of the time limit, in today's talk, we have to only focus on three pieces of work, respectively related to design pattern and CPS testing. And we will see how hybrid automata technology contributes to these three pieces of work. Okay, so I'll skip the applications. Without further ado, I'll dive into these specific works. Our first piece of work is published in TPDS 2015. Okay. This work, so a least-based hybrid design pattern for proper temporal embedding of wireless CPS interlocking. The background for this piece of work is actually from medical CPS. The demand to use interconnected and interlocked smart medical devices to increase safety. Specifically, the demand comes from the laser tracheotomy surgery. Okay. So in this kind of surgery, we're using a laser scalpel to cut open a patient's trachea. Okay. And for this kind of surgery, the patient is under the influence of anesthetics. Therefore, he or she cannot breathe by himself or herself. We need to use a ventilator to pump oxygen into the trachea of the patient. So now imagine this situation. Okay, so if there is trachea, if there is oxygen in your trachea, and there is also a laser that tries to cut open your trachea, what will happen? This is what will happen in the operation room. This kind of so basically the laser will set fire onto the patient's trachea. And unfortunately, this kind of accident happens quite often. When we were doing the survey, it's about once every month around the world. So fundamentally, this kind of accident could be avoided if there is effective interlocking or mutual exclusion between the behaviors of the laser scalpel and the ventilator. So basically, when you want to shoot laser, the ventilator must be paused, stopped pumping oxygen into the patient. But for the time being, okay, so the smart device of laser scalpel, the ventilator, and the vital sign sensors, we have all of these devices in the operation room, but they are not mutually interconnected or interlocked. We still need human being to manually remember what is going on, to carry out the interlocking, the mutual exclusion protocols. So if you want to shoot laser, then you need to first stop ventilator. And then the ventilator cannot be stopped forever, because if you stop forever, then patient will be suffocated to death. So after you're shooting laser for a certain while, you need to stop the laser and then restart the ventilator. So the human being, the surgeons and nurses in the operation room have to remember everything. But human beings are prone to error. So if they make errors, then they violate this protocol, and then accidents will happen. So this kind of accidents, people think that we may be able to avoid them, okay, if we can interconnect all these smart devices, okay, to carry out mutual exclusion, to carry out interlocking, okay, in the future. And what is more, people want to use wireless links to connect these smart devices. And why is that? Ironically, it is for safety. Because nowadays, operation rooms are already a mess. We have tens or even hundreds of various kinds of smart devices and all kinds of tubes, power cords, okay? Already a lot of wire connections between some of these devices. And if we want to introduce even more connections, wired connections between devices, this will make the situation more messy. And so many wires are actually a hazard for safety, because people can trip over these wires and cause accidents. Therefore, people want to have this kind of future operation room where all the smart devices are connected wirelessly. Okay. So demand to use wireless links for safety and efficiency concerns in the operation room to interlock, to interconnect the smart devices. But wireless communications, by its nature, are unreliable. Wireless links can fail due to various kinds of reasons: multipass, blocking, wireless interference, or jamming. Okay. They can all cause wireless links to fail and wireless packets to be lost. So on the one hand, we want to use wireless to connect devices to enforce safety. On the other hand, the wireless links themselves are not stable. They can fail arbitrarily. Then how can we guarantee safety? Actually, it is proven that for certain kind of safety requirements, If the wireless links can fail arbitrarily, then such safety requirements cannot be guaranteed. Okay. For example, the two general problem. It's already proven that if the wireless link can fail arbitrarily, the two generals problem has no solution. But fortunately, for our laser tracheotomy scenario, okay, we only need to guarantee a certain subtype of safety rule, the so-called PTE safety rule, proper temporal embedding safety rule. For this kind of safety rule guarantee, we discover that later. We'll show that even though wireless links can fail arbitrarily, we can still guarantee its safety. So how do we do that? So let's first start from understanding what is proper temporal embedding safety rule, PTE safety rule. So again, we use this laser tracheotomy as the example to illustrate the idea of PTE safety rule. So basically, in laser scalpel, in laser tracheotomy surgery, the duration that the laser scalpel shoots laser should be properly embedded into the duration that the ventilator is pausing. So the laser scalpel has two states: shut-off state and shooting laser state or emission state. The ventilator has two states: the ventilating state, where it pumps oxygen into the patient's trachea, and the pausing state. So the duration of shooting laser should be properly embedded in the duration of the pausing of the ventilator. What is more, we're not just talking about logical time embedding. The real time also matters because of physical system constraints. So first of all, the risky state dwelling time should be upper bounded. So the ventilator can be paused, but the duration for pausing the ventilator must be upper bounded. The T3 must be upper bounded, because if you pause it forever, then the patient will be suffocated to death. So correspondingly, because T3 has upper bound, T4 also has a upper bound. You cannot shoot laser forever. It must be embedded within T3. T4 must be in duration must be embedded in T3. Secondly, after you have paused the ventilator, you cannot immediately shoot laser because there's still oxygen left in the patient's trachea. You need to wait for a certain amount of time, for example, 10 seconds, to wait for the oxygen to be exhaled naturally by the patient. And then after this, at least 10 seconds duration, only after that can you start shooting laser. Similarly, when you stop shooting laser, you cannot immediately start ventilating because the trachea is still hot. And if you pump oxygen into the trachea, there can still be fire. So after stopping shooting laser, you need to wait for another, at least, say 5 seconds before you can start ventilating. Okay, so not only the T4 needs to be properly embedded in T3, there's also duration, the real-time constraints. Upper bound T4 and T3 needs to be upper bounded. T1 and T2 needs to be lower bounded by certain constants. Okay. So this is the idea of PTE safety rule. Of course, the mathematical formal description of it is much more complex than this, but you get the idea from this example. Okay, so if the communication link between laser scalpel and ventilator is through wireless, and the wireless communication can fail arbitrarily, how can we still guarantee safety rule? Fortunately, we discovered that this is doable, unlike the two general problem. For this problem, PTE safety guarantee is doable. The solution heuristics, okay, is there a design pattern that can guarantee PTE safety despite of arbitrary wireless link failures? Okay. The heuristics comes from the leasing philosophy, leasing design philosophy. It is a design philosophy for distributed systems. And then we are going to use hybrid automata as the formal tool to describe our design and to analyze our design. So first, what is the leasing design philosophy? we can use an analogy to give you a feeling of what is leasing. It is a general concept of leasing design pattern for CPS PTE guarantee. With the analogy is about a musical event, how to organize a singing event. So to organize a singing event, we have various kinds of roles. We have the singer, which will be the proposer or initiator of this event. We have the manager or supervisor to organize this event. And we have various kinds of resources, like the venue for the singing event. We also have like electricity, the power company, also involved in this event. They are called the participants for this event. So initially, the singer or initiator needs to request to the supervisor that I want to sing an event. And then the supervisor needs to lease all kinds of resources needed to contact the participants to lease the resources. It needs to contact the venue, say I'm going to lease the venue on Sunday from 9 a.m. to 11 p.m. Sign a contract. Okay. And then lease the electricity. Say I want the electricity on Sunday from 10 a.m. to 10 p.m. Okay. Only after the manager, the supervisor has leased all the needed resources, sign all the contracts, the leases, then can he reply to the initiator to approve this event. And then on Sunday, okay, all these activities in the participant, in the initiator, can be carried out automatically without need to communicate with each other. So starting from 9 a.m., the venue is ready, and it will be ready until 11 p.m. Starting from 10 a.m., the electricity is ready, and it will be ready until, say, 10 p.m. And then the singer can sing, okay, starting from 6 p.m. to 8 p.m. Okay. So even without the communications between all these entities, the event can happen naturally. You don't need to worry that the electricity will gone out in the middle of the event. Don't need to worry about that. But of course, there will be some waste. Okay? So you stopped early, but because of lack of communication, you still need to wait for, say, 2 hours before the electricity is gone. And then you need to wait for another 1 hour before the venue is gone. Okay? So it's kind of a waste. If you can successfully communicate with each other, you can release the corresponding resources much earlier. So the user experience can be better, the efficiency can be better. But if you do not have communications, although the efficiency, you lose some efficiency, but the safety guarantee is still there. Okay. So this is the philosophy of the leasing design pattern. So correspondingly, for the laser tracheotomy, we can enforce this kind of philosophy. Okay. So basically, we have 3 kinds of roles in this design pattern. We have initiator, we have supervisor, and the participant. The surgeon, together with the laser scalpel, plays the role of the initiator in this case. And then we have a supervisor computer, which is connecting all the smart devices in the operation room. And then the ventilator takes the role of participants. So whenever the laser scalpel needs to shoot laser, it needs to request to the supervisor, and the supervisor will sign a lease with the ventilator. So the ventilator will pause for a certain duration, and within this duration, the laser scalpel can shoot laser. So this is the overall idea. It's easy to understand. It should work, but there are many details because we need to guarantee these detailed temporal requirements. Like these. Okay? So these detailed temporal requirements, we need to satisfy them without communication, okay? With arbitrarily failing wireless communications. So to guarantee all of these, although the philosophy is simple, the design is non-trivial. So finally, we have the 3 automaton, respectively for the role of supervisor, initiator, and participants. So this is the hybrid automaton for supervisor. And this is the sketch for you to understand it easily. So in this case, we are dealing with N participants for the PTE safety guarantee. And then during the middle of the operation, the initiator can cancel the lease. People can cancel the lease. And if the supervisor finds there are some urgent situations, the supervisor can also abort the lease to abort the event. So it can be proactively stopped by the initiator, then can also be passively stopped by the supervisor if the supervisor sees some situation that is not good. But also, if there is communication failures, this event can also be stopped because of the detailed designs. And this is the hybrid automaton for initiator. And then this one is the hybrid automaton for the participant. So the details of the hybrid automata are non-trivial, but I want to point out several things. So first of all, we have models for the arbitrary failure of wireless communication. So this double question mark means that the corresponding event is a message reception event. And this message reception event may fail arbitrarily because of wireless packet loss, arbitrary wireless packet loss. So all of these reception events are denoted by this double question mark, indicating the message could be lost arbitrarily. Secondly, we are using the hybrid automata's differential equations to describe the flow of time. So this is continuous behavior, the flow of time. And thirdly, in the hybrid automata, we have various kinds of configuration parameters. Typically, the temporal upper bounds for various kinds of locations. So these upper bounds, they are configurable parameters during configuration time. They are constants during runtime, but they are configurable before you run the system. Okay, so this is for every hybrid automata. We have these. So for example, in the initiators, we also have this double question mark. We have configurable parameter. We have flow of time. For the supervisor, we also have these double question mark indicating arbitrarily indicating this wireless packet message can be arbitrarily lost. And we have flow of time. We have configurable parameters. Right. So the important thing is that we prove if the temporal parameters of the design pattern hybrid automata satisfy a certain set of linear inequalities, then PTE safety is guaranteed despite of arbitrary communications link failures. And we prove that. And this is the set of the inequalities. There are linear inequalities of the configuration parameters. So these are the configuration parameters encountered in all three hybrid automata. And if they satisfy these constraints, then we can guarantee, even though the wireless communication links can fail arbitrarily, the wireless packets can be lost arbitrarily, PTE safety is always guaranteed. There could be some efficiency loss. There could be some user experience degradation. For example, the user needs to, although the laser scalpel stopped shooting laser a while ago, you still have to wait for the entire lease to expire before the ventilator can restart. So this is kind of user experience degradation, but the safety of the PTE is still guaranteed. The patient will not be suffocated to death. The fire can never happen. Okay, so these hybrid automata, they are still, we can regard them as design templates. We haven't, so there's the further step question is that how to turn these design patterns into detailed CPS designs. So we have another theorem proven. We propose a formal procedure to elaborate a design pattern hybrid automaton into a detailed design hybrid automaton. Okay, so for example, this is the original hybrid automata. It has two states, fallback and risky. It's a quite simple automata. Using our formal elaboration procedures, we can expand this hybrid automata into a full-fledged detailed design for the application. We further proved that if detailed design hybrid automata are respectively derived by elaborating corresponding design pattern hybrid automata, then the PTE safety is guaranteed despite of arbitrary communications link failures. So if we follow this elaboration rule, then the PTE safety is still guaranteed. Okay? No matter how the wireless communication link fails. Okay, so in this way, the design pattern can be expanded into detailed designs. All right, so to evaluate, to verify the correctness of our analysis, we also carried out experiments to verify our proposed design pattern. So basically, we are emulating mimicking the laser trachea surgery. Okay, so the first author played the role of the patient in this evaluation. Okay. Of course, we cannot really cut open his trachea. So what we do is that we have a ventilator simulation computer. In this computer, it will display inhale, exhale, hold your breath, this kind of commands to mimic the ventilator's behavior of pumping oxygen, exhaling, and then pausing the ventilator. Okay. And then our first author is following the instructions on the screen. Okay. So if the instruction says inhale, he will inhale. The instruction says exhale, he will exhale. Instruction says hold your breath, he will hold his breath. Okay. And then we have another computer to simulate or mimic the behavior of the laser scalpel. It will spontaneously request to shoot laser, okay? Request to the supervisor, and the supervisor will run the leasing protocol to ask the ventilator to pause for a certain amount of time. And these three entities, they are connected through wireless communication links. And in addition, we also have a wireless jamming source, interference source, constantly try to jam the two wireless links between the ventilator supervisor and the laser scalpel. And here is the evaluation results. So we run 3 trials. Each trial lasts 30 minutes. And then for 2 of the trials, we carry out this PTE design pattern, this lease-based design pattern. 2 other trials, we do not carry out the design pattern. We use the naive communications, packet communications between the 3 computers. And then during the 30 minutes, the laser scalpel will spontaneously request to shoot laser and to emulate it wants to simulate it wants to shoot laser. And then for these 2 trials, the duration, the expected duration of shooting laser is 18 seconds. So it requests many times throughout the 30 minutes of the trial. For these 2 trials, the expected duration for shooting laser is 6 seconds. And then the expected duration between 2 shooting of lasers, there are 30 seconds. So for each trial, the laser scalpel simulating computer will request several times. So this is how many times it requested. For this trial, it requests 19 times. This one, it requests 11 times. For this one, it requests 19 times. This one requested 12 times. This column is important. Number of failures. How many times in the corresponding trial that PTE safety rule is violated. So we can see that using our leasing design pattern, there is 0 failures, 0 violations of the PTE safety rule. This one, 0 also. But if you do not use our design pattern, for this trial, the PTE safety rule is violated 4 times. For this trial, the PTE safety rule is violated 3 times. So every time it's violated, there is a risk of fire. The patient is in danger, in lethal danger. And then this column shows how many times the lease protocol or design pattern kicks in to save the situation. So the reason why we have 0 failure is because the lease design pattern kicks in 5 times to save the situation. In this trial, the lease design pattern kicks in 3 times to save the situation. So to guarantee the safety. Okay, so this is this piece of work. Next, let's talk about the testing issues. The related work is the work that we published in ACM Transactions on CPS 2019. Cross-domain noise impact evaluation for black box 2-level control CPS. The demand comes from evaluating the impact of cross-domain noise in control CPSs. Control CPS is a major category of CPS. A typical architecture for control CPS is what we call the 2-level control CPSs. In here we have the cyber subsystem and a physical subsystem. At the core of the physical subsystem is the physical plant to be controlled. Typically, it is a mechanical machinery, for example, an airplane to be controlled. And then formally, the plant to be controlled can be abstracted by its state space, the state of the plant vector. It is a vector in the state space. For example, if the plant is an airplane, then the state vector could be the XYZ coordinates of the airplane in the 3D space. And then this plant state is periodically sensed by the sensing module of the cyber subsystem. The sensed state, together with the noise of the sensing, are sent together into a network of interconnected modules. So noise here created by this sensing is what we call the cross-domain noise, because it is generated when the state information crosses the domain of physical subsystem from the physical domain into the cyber domain. And then this noisy sensed data, sensed state of the plant is sent into this interconnected digital, not interconnected network of the digital modules to generate the final decision from of the cyber subsystem. So the final decision is what we call a reference point. Reference point actually means the intended state that we want the plant to reach in the next period of the control, the bigger control loop. This reference point, denoted by O reference prime, is when it enters, it crosses the domain again from the cyber system into the physical subsystem. First, it's bounded, it's filtered by the bounding filter. The main purpose of this bounding filter is to make sure that the change of the reference point cannot be too drastical. It has to be bounded by a certain limit. And then the output from this filter is what the actual reference point for the next period sent to the inner control loop. inner control loop in here. So here first it is minused by the local sensed plant states, and then the result, the difference, is what we call the error of control. That is the deviation from the actual state and the intended state. And then this error is sent to the local controller to guide it to maneuver the plant state toward O reference prime prime. And then this is the entire control loop. So for the local controllers, typically it is a linear controller. If that is the case, the two-level control CPS can be abstracted, can be modeled using this kind of very simple hybrid automata. So basically, every period, there will be a reference point update event. And then O reference prime prime is assigned a new value. Within this location, the difference between the current state of the plant and the reference point, the intended state, the error, what we call the error, its dynamic, its derivative is controlled by F times error. F is a matrix, a constant matrix determined by the design of the controller. Typically, it's a linear controller, then F takes this form. There are some mathematical backgrounds, but they are not important. It's important for you to know that we can model the entire two-level control CPS using this kind of hybrid automata. Every period, the O reference will be updated by the new input from the cyber subsystem. And after that, during the whole period, the continuous dynamics of the plant is controlled by this differential equation. And also time flows continuously. Okay, so for this kind of abstraction for the two-level control CPS, how do we evaluate or profile the impact of noise, cross-domain noise N, the N created in here? So basically, if our sensing of the plant state is erroneous, then it will affect the final decision. If the final decision is imperfect, it will affect our control result. So how to profile the impact of N to the control results? In this piece of work, our major concern is the probability to reach forbidden regions. Or in other words, the reachability issue in the hybrid automata. So what is the probability to reach forbidden regions? For many control CPS, the major concern is whether or not the plant state can reach certain forbidden states. For example, if the plant that we control is an airplane, and the state is the XYZ coordinate of the airplane, then a natural forbidden region is that the region where the Z coordinate is below 0. If the state of the airplane reaches such regions in the state space, that basically means the airplane crashes onto the ground. Okay, so this kind of thing can never happen, must never happen. We can say the concern is whether or not the state can reach the forbidden region. Okay, it is a typical reachability concept in hybrid automata model checking. So because of this, for this kind of concern, we can use reachability concept to profile the impact of the cross-domain noise. Formally, we can define the impact of noise N to be just change of reachability to forbidden regions. So we have this notion, given the initial state of the physical plant at time 0, which is denoted as x0, and given this cross-domain noise random variable n, Pn x0 is the reachability of our hybrid automata to the given forbidden regions, the probability, the reachability. So P0 x0 means that when there is no noise, no cross-domain noise, what is the probability that starting from the initial state of x0, the plant of the control CPS reaches forbidden region? So the reachability difference is what we define as the impact of noise n when the initial state of the plant is x0. So the holistic vision of the holistic profile of the impact of cross-domain noise n would be a collective sample of this in x0. x0 is randomly sampled from the entire state space. We define this collection of samples of I to be the profile of cross-domain noise. And we call it I to be the impact. And given x0, given the random noise, random variable of n representing the cross-domain noise, the impact becomes a, we can evaluate it to give a fixed value for it. And then when we have a collection of samples, we can have a collection of I's. We can have statistics about I's. And then through this statistic, we can understand the impact of cross-domain noise n. But here is a pitfall in this definition. So to retrieve a holistic picture of the I's distribution, we need to sample the entire state space, which is huge. There will be too much work if we need to sample the entire state space. So for example, if it is the airplane and it can fly thousands of kilometers across the world, then the entire state space will be the entire atmosphere of the globe. Okay? Then it's too much work. Okay? So is there any way to shrink the workload? We do not need to sample the entire state space. We only need to sample a portion of the state space. Is it possible? If we can do that, we can drastically reduce the workload. We notice that the solution lies in the bounding filter in this two-layer control CPS architecture. The bounding filter limits the magnitude of reference point change for every control period. So mathematically speaking, this means given the initial state of the plant x0 in the state space is a point, then every period, the change of the reference point, okay, the difference between the new reference point and the initial state of the plant, because of the bounding filter, the difference is bounded by a hyperbole. Okay? It cannot exceed this hyperbole. And then in control theory, okay, we have this notion of Lyapunov stability. So we are assuming that the control is classic linear control, which is the widely adopted control strategy. Okay? And then for linear control, usually people will design the system to be Lyapunov stable. So because of this Lyapunov stability theory, okay, and because the change in every period, the reference point change is limited by this hyperbole, then we have this kind of feature. Okay? All trajectories from given initial states are also bounded. For example, if the new reference point is O2, is O1, okay, then the future trajectory of the state of the plant will be limited, will be bounded by this ellipsoid, hyperellipsoid. Okay. If the new reference point is O2, then the future trajectory of the state of the plant will be bounded by this ellipsoid. Okay. If the future reference point is O3, then the trajectory is bounded by this ellipsoid. Okay. So no matter which ellipsoid, as long as the new reference point is within this ball, we can see that the trajectory is bounded by one of the ellipsoids. Okay. And then these ellipsoids have a boundary, okay, have an upper bound. Therefore, it inspires us. So if the forbidden region is given, okay, and then the initial state is given, and then the bounding ball radius is given. Okay, radius is given. Then the future trajectory of the state of the physical plant is bounded. Okay. It cannot go too far away. Therefore, basically, the intuition is that if the forbidden region is within the solar system, okay, do we need, and we are studying the reachability of our spaceship hitting into this forbidden region in the solar system, do we need to really consider the initial location of the state space and in some other remote galaxies? We do not need to. Okay? We do not need to sample the entire universe in order to study the reachability of our spaceship hitting into the forbidden region inside of the solar system. We only need to sample nearby the solar system. That's enough. So how far away is far enough? Okay. And farther than that is not necessary. For this, we need to study the trajectory bound. And then we find the formula to calculate the bounding radius, gamma, big gamma. Okay, so given the initial state, any initial state x0, given that the new reference point is within small gamma, we derive the formula using the Lyapunov stability theories in control, okay, which can bound the future trajectory of the physical plant. Okay, so if your reference point is within this hyperball, then the future trajectory will never exceed this big ball. Okay. And then beyond this big ball are the unreachable regions. Okay. Therefore, if our concern forbidden region is this, then we only need to sample this gray area in the state space, because beyond this gray area in the state space, any initial state x0 beyond this gray area, say here, okay, its future trajectory is bounded by a ball of radius gamma. Therefore, it can never reach the forbidden region. Okay. Only initial states within this gray area whose thickness is gamma, they have this risk of touching forbidden region, reaching forbidden region in the future. Okay. So in this way, the sampling space is shrunken from unlimited space to this limited space, okay, within gamma vicinity of the forbidden region. We only need to sample test cases in this gamma vicinity. Okay, so all these analysis is based on the hybrid automata reachability analysis. We have also carried out experiments to evaluate our proposed approach. Because of time limit, I'm not going to dive into the details of this evaluation. Interested audience should refer to our paper for the details. Okay, so this is this piece of work. When we talk about testing. Naturally, the related issues are Oracle and debugging. So our next piece of work, the paper published in ICSI 2019, talks about Oracle issues and debugging issues in Control CPS. And this is the specific paper, a system identification-based Oracle for Control CPS software fault localization. So unlike traditional control software, nowadays Control CPS software can have millions of lines of code involving complex libraries, for example, computer vision. So for such complex control CPS software, using the traditional manual way to debug it is no longer sufficient. We need the help of automated tools. In software engineering jargons, we need help from the software fault localization, SFL tools. SFL means you want to locate which line of the source code could be buggy, could be the cause of the bug. So according to a recent survey, that survey published in Transactions, IEEE Transactional Software Engineering 2016, we have already more than 330 various kinds of SFL tools to help human beings to automatically locate the suspicious source code lines. And these hundreds of SFL tools can be categorized into 8 families. So the most mainstream family is the spectrum-based SFL. And then we have also other types. According to the survey, hundreds, more than 40% of all these surveyed SFL tools need oracles. So what is Oracle? Oracle is a mechanism to judge output correctness without looking into the source code. So you give me the input, and then I view the software to be a black box, and I look at the output. I will immediately know, the Oracle will immediately tell you whether or not the output is correct or wrong. So the typical workflow of those SFL tools using oracles is like this. So first you have the source code. There could be some latent bugs in the source code. Okay. For example, these italic source code blocks, they are truly buggy. But we don't know, human programmers do not know that yet. Okay. So how to discover these lines, to locate these lines? What we need is a bunch of test cases. Okay. We have M, various test cases, test case inputs, okay, many of them. And then we will execute the program using these test cases. Okay. So these test cases are known to the programmer. The source code is known, but exactly which line of the source code is buggy, the programmers do not know it. So we execute it, and we log the source code execution trace. And also we log the test case output, corresponding output. And then these logs will be sent to the Oracle. The Oracle, based on the input and output, can decide whether or not these outputs are correct or incorrect. So can label it. Okay. So the Oracle can label the test case source code execution trace. Okay. Corresponding execution trace can be labeled. So say if Oracle decides that this output is wrong, then it will label this source code execution trace to be incorrect. If the Oracle thinks this output is correct, it will label the corresponding source code execution trace to be correct. Okay. So after this process, the Oracle will output the test case source code execution trace and its label, either labeled as correct or incorrect. And for M input and M output, we'll have M labeled execution traces. And then all these execution traces will be sent to the software fault localization tool, SFL tool, various kinds of SFL tools. And then these SFL tools will generate an SFL results reports. So the result is basically a list of suspected source code blocks in descending order of suspiciousness. So, for example, say the SFL tool give this kind of report. It says the source code based on this input, these labeled execution traces, I think source code block number 2 is the most suspicious, and then followed by block number 1, and then followed by block number 5, followed by block number 6. So this will be the SFL report, and this report will assist the human programmers to locate the true bug. Okay, so based on this suspicious list, I can purposefully check the corresponding source code to see whether there's a bug or not. However, the Oracle design difficulty is very much application dependent. For some applications, Oracle design can be very easy. For example, sorting. Okay. Sorting Oracle design can be very easy. I give you a bunch of number, and then you give me an output. The sorting program give me an output. I only need to look at whether or not this output are sorted or not. Then I can decide whether or not there's something wrong happening in the software execution. Okay, so you give me a number like a bunch of integer values, and then the output is 1, 3, 5, 2, and 7. So I see that it's not purely ascending. Then something is wrong with the sorting, definitely. Okay, so sorting program Oracle design is very easy. However, for many other applications, the Oracle design can be extremely difficult. It's so difficult that we have a term, the Oracle problem in software engineering. We talked about the difficulty of Oracle design. Control CPS, unfortunately, belongs to one of the domain where the Oracle problem is very serious. Okay, so it's very difficult to design oracles for Control CPS. The reason is the reason actually is simple. Okay, so I give you this illustration, I can immediately understand it. So say we are going to debug a avionics software, okay, that controls the flight of a airplane. Okay. So airplane takes off from location E and landed in location F. Okay, so this is the trajectory of this airplane, dotted trajectory. And then you fly it using another software, and then the airplane takes off from E and landed in F safely, but with another trajectory. So now, how can you tell me which trajectory encountered software faults? It's really difficult to judge, because for Control CPS, the output is the physical trajectory of the plant. And this trajectory can be, does not have to be unique. Okay? There are various ways to fly from location E to location F. Okay? Even if you landed safely, it doesn't mean that throughout the flight, you never encountered software faults. Okay? So how can you judge which trajectory is buggy? Okay? It's really difficult. So in practice nowadays, still, we are extensively using human oracle to determine the correctness of the control CPS output, which is the physical trajectories of the plants. Okay. Human oracle basically means that we need to convene a panel of experts, human experts, sit together and look at the trajectories, and then decide which trajectory is morbid, which trajectory seems to be correct. Okay, so human manually label the correctness. This is the current practice. Apparently, this practice is not ideal. Okay, so depending on the availability of the experts, the oracle quality can be ad hoc. Okay? And also, it depends on the expertise level of the experts. So is there a way to find a better oracle, or a more deterministic, more reliable oracle for an automatic oracle for control CPS SFL. This is the key problem that we want to address in this research. So we find the heuristics to the solution is this. Okay, so system identification, SI, is a we discovered that system identification, SI, is a well-established research area to predict control systems behaviors. There are many various kinds of system identification algorithms. Among them, one of the most widely used SI method is autoregressive system identification, RSI. Basically, it means linear regression. So we look at the past trajectory of the physical plants, and then we can use linear regression to periodically look at the past trajectory of the plants, and we can periodically predict the future trajectory of the plants. So if this periodical prediction, if the actual future trajectory deviates slightly from the predicted trajectory, then we regard there is no abnormalities in the control CPS. But if for some period the projected trajectory and the actual future trajectory, they have big deviations, then we regard there's something wrong in the execution of the control CPS. So this is a very straightforward and simple idea. So now the question is that, is this idea good enough to serve the purpose of Oracle? We plan to evaluate this proposed Oracle empirically, using empirical method. So we propose to use ARSI prediction as the Oracle for control CPS SFL, basically control CPS debugging. And this is the formalized details of the method. Okay, so basically linear regression. We use, when the control CPS is running, we in parallel we run the ARSI or linear regression based prediction of the trajectory. And if the actual trajectory deviates drastically from the prediction, then we think that there is something wrong. Okay, so our Oracle thinks there's something wrong with the control CPS. So the details, you can refer to the paper for the details, but the idea is this. Okay, so how good this Oracle is, we have to evaluate it empirically. Okay, so before evaluation, we need to determine the metrics that we want to evaluate. We propose to evaluate these metrics. First is accuracy. Accuracy is defined as the number of truly buggy suspects in the SFL report, okay, list S, okay, divided by the total number of suspects in the report. Okay. So for example, in this report, okay, it points out that source code block 2, 1, 5, and 6, they are the suspects. But the ground truth is that block 5 and 6, they are truly buggy. Block 1, 2, they are not buggy. Then the accuracy of this report is 2/4. Therefore, it's 50%. Another metric is the latency, the so-called latency. Basically, it means the index of the first truly buggy suspect in the report S. For example, in this case, the latency of this SFL report is number 3. Starting from the number 3, we hit a truly buggy suspect. And also, we not only care about the SFL results quality, we also care about the Oracle's raw quality. This raw quality is measured by the false positive and the false negative rates of the Oracle compared to the ground truth, okay, to measure raw Oracle quality. The rigorous definition can be found in the paper. So basically, among the true negative, okay, how much of them, what is the percentage of them, they are labeled as positively wrong trajectories. Positive means that the trajectory is labeled as incorrect trajectory. Among the true positives, what is the percentage that are erroneously labeled as negative? So this is the false positive and false negative rates of the oracle. They reflect the raw quality of the oracle. All right, so the research questions are, question 1, how does our proposed approach impact SFL quality, measured by accuracy? Okay. Correspondingly, we also define another measure called recall, but these two measures, they are related, so just evaluating one is enough. And then measured by latency. Second question, how does our proposed approach impact raw oracle quality, measured by the false positive rate and false negative rate? So to carry out our empirical evaluation, we need control CPS testbeds. The testbeds we choose there are two testbeds. One is ArduPilot. ArduPilot is an open source platform to build various kinds of control gadgets, control CPS devices. It includes actually 4 kinds of device. The quadcopter, the UAVs, okay, the drone, quadcopter drones, and then also the fixed wing UAVs, unmanned aerial vehicles, and also the boats, and also the submarines, okay, and also the vehicles, land vehicles. The cyber subsystem entirety of the ArduPilot is more than 1.4 million lines of code, of source code, and more than 9,600 files. The cyber subsystem application layer is about 27K lines of source code, okay, 160 files. So it is a reasonably big control CPS, and it's open source. Another testbed is the computer vision guided inverted pendulum maneuvering testbed, IPCV testbed. IP for inverted pendulum, CV for computer vision. So here in this testbed, we are using computer vision, the cyber system subsystem, using computer vision to detect the current state of an inverted pendulum, and then carry out remote control of the inverted pendulum. An inverted pendulum is a cart that can move along a x-axis, and then on the cart there is a metal rod with one end hinged on the cart. So the cart moves back and forth to keep the iron rod, the metal rod, standing upright still. That's the purpose, control purpose. So this this testbed, its cyber subsystem is about 4K lines of source code. It's developed by our own research team. 11 files. So this is a relatively small scale control CPS. So evaluation, bug sets, and buggy versions. So we have 40 buggy versions, aka subjects, of the ArduPilot are created using real-life bugs. So ArduPilot has a very complete GitHub log of its development. So we got real-life bug information from that log. Okay, so, and we created, using these real-life bugs, we created 40 buggy versions of, aka subjects of ArduPilot. And then we also created 61 buggy versions, aka subjects of ArduPilot, using artificially injected, well-known common bugs in the field. So this is based on a survey in IEEE Transactions on Software Engineering survey paper, I think also published in around 2016. So this survey paper surveyed the common bugs in the field, and it proposed that there are about 12 or something kinds of very widely seen common bugs in the field. And so we, based on this survey, we created our own artificial bug and then inject them to create these 61 versions, buggy versions of autopilot. And for the IPCV testbed, we also created 12 buggy versions of it using artificially injected well-known common bugs in the field based on this survey's advice. So these two are using artificial bugs. This one is using real-life bugs. And these are the evaluation results. Okay. In this diagram, we compare the accuracy of the 40 buggy autopilot subjects with real-life bugs. The x-axis are the combination of the oracle that we use and the SFL algorithm that we use. PA represents our proposed ARSI oracle. HA represents the human oracle approach. Okay, so we actually invited a group of experts to give the criterion to judge the correctness of the trajectories. The details are in the paper. TA means Tarantura SFL algorithm. This is the representative algorithm in the SFL family of program spectrum-based SFL. CR means crosstab SFL algorithm. This is the representative algorithm in the statistics-based algorithm family, SFL algorithm family. NN means back pressure neural networks SFL. This is the representative algorithm in the machine learning-based algorithm family, SFL algorithm family. The y-axis is the accuracy. The higher, the better. We can see that using our proposed oracle, the accuracy is apparently better than using the human oracle when we are using Tarantura. Using crosstab, the same observation. Okay? Our proposed oracle performance is better than the human oracle. For neural networks, the difference is not apparent, is not significant. We suspect the reason is because neural networks need big data. And here we only have 40 buggy subjects and 120 trials. This is not big enough. That's the reason why neural network is not really taking off. Right, so the next diagram compares the latency. The smaller, the better. The x-axis is the same. The y-axis now is the latency. The smaller the latency, the better. We can see that using our proposed oracle, the latency is shorter than those using human oracle in Tarantura. In crosstab is the same thing. Okay. Neural network, again, the difference is not significant. This diagram compares the raw quality metrics, the oracle false positive rate and false negative rate. Okay. We can the x-axis is the same. PA represents our proposed oracle. HA means human oracle. FP means false positive rate, and FN means false negative rate. The y-axis is the value of the false positive or false negative rate. The smaller, the better. We can see that using our proposed oracle, the false positive rate is smaller than using human oracle. The false negative rate is also smaller than using human oracle. Similar observations can be made for the other two test beds, 61 buggy versions of autopilot using artificial bugs, the accuracy comparison, the latency comparison, the false positive rate, false negative rate comparison, the 12 buggy versions of IPCV subjects with artificial bugs, same observations, accuracy, latency, false positive rate, false negative rate. We also evaluate the p-value and ES value of these comparisons. P-value basically means the probability that the comparison differences are only by chance. So the smaller the p-value, the more convincing the comparison is. Okay, so usually less than 5% p-value is good. ES value measures the magnitude of differences. Usually is the bigger the better. Usually if it is bigger than 0.4, the comparison is good. In here, we can see that most of the comparisons, aforementioned comparisons, their p-value and ES values, they are in good range. So these comparisons, they are convincing. For neural networks, the comparison is not so convincing, mainly because it's not big data enough. This is for the autopilot real bug comparisons. Autopilot artificial bug comparisons, similar observation. IPCV artificial bugs comparisons, similar observation. So in conclusion, For research question 1, how does our proposed approach impact SFL quality measured by accuracy and latency? Our result is, compared to the human oracle approach, our proposed approach, ARSI oracle, significantly improves the quality of TA and CRSFL in terms of accuracy and latency. The magnitude of improvement is medium to large. The research question 2, how does our proposed oracle approach impact raw oracle quality measured by the false positive rate and false negative rate? The conclusion is that compared to the human oracle approach, our proposed approach, ARSI oracle, significantly improves the raw quality of the oracle in terms of false positive, false negative rates. The magnitude of improvement is large. Okay, so due to the time limit, in today's talk, we can only present three pieces of our work, number 4, number 2, and number 1. If you are interested in the details, in more details, and other works of ours, you are very much welcome to visit our website, www.comp.polyU.edu.hk/CSQWANG. And you are welcome to ask questions during the Q&A session. Thank you very much.